Okay, we know that the electric field intensity due to a point charge is given by Q over 4 pi epsilon 0 r squared. So this is the electric field intensity due to a point charge. But what if we have more than one point charge in space? So we have a point charge Q1 here and another point charge Q2 placed here. All these point charges will contribute to an electric field at any arbitrary point P. So the electric field at this point will be having that direction. Let's say the electric field intensity due to Q1 will also have the electric field intensity due to Q2 and many other electric fields that we may have. Remember, electric field is a vector quantity, so the total electric field intensity at that point, the total electric field intensity will actually be the vector sum of the electric field intensities. So if I could add the vector sum of the electric field intensity due to Q1 plus the vector sum, plus the vector of the electric field intensity due to Q2, that would give me the electric field. So that's the so-called principle of superposition of electric fields, and we're going to be applying it to solve most of these problems involving electric field intensity. Okay, let's begin. So we have point charges of 4 microcoulombs and negative 6 microcoulombs, and I want to find the electric field intensity at point P. So let's look at this in a vector diagram. So the electric field intensity due to the 4 microcoulomb charge at this point is actually going to be, this is a positive charge, so electric field intensity is the force per unit positive charge. So we assume there is a charge of +1 coulomb placed here, so plus and plus will actually repel each other. So that's the direction of the electric field intensity due to Q4. I'm going to call that E4. Also the electric field intensity due to the negative 6 microcoulomb charge. Since this is a negative, the electric field intensity will point to the left. So allow me to call that E6. Okay, there we go. So let's calculate the resultant electric field intensity, beginning with the electric field intensity due to Q4, the charge of 4 microcoulomb. That's going to be 4 microcoulombs. So okay, just to begin with the electric field intensity of any point charge given by Q over 4 pi epsilon 0 r squared. So the electric field intensity due to the 4 microcoulomb charge is going to be, I summarize all this of course to the common formula, K times Q divided by R squared, where K is 9 times 10 to the power 9, assuming we're working with free space or vacuum. So our charge is 4, then our K is 9 exponent 9, our charge is 4 microcoulombs. Don't forget to change that to coulombs. The distance from 4 microcoulombs to point P is 5 centimeters plus 2 centimeters. That's a distance of 7 centimeters. So 7 centimeters, that's 0.07 meters. Okay, I've got to square that. Okay, so let's see what we get. If you put this on the calculator, you get approximately 7.347 exponent 6 newtons per coulomb. That's the electric field intensity due to Q4. Let's do that also for the electric field intensity due to the negative 6 microcoulomb charge. That's going to be 9 exponent 9 times 6 times 10 to the power negative 6. I change the 6 microcoulombs to coulombs. Of course, I don't indicate the negative sign here because I will take care of the direction using the vector diagram. The distance between the negative 6 microcoulomb charge and the point P where we are finding the electric field intensity is 2 centimeters, that's 0.02 meters. So if you plug these values into the calculator, you have 1.35 times 10 to the 8th power. Okay, guess that's it. Okay, got to prove that perhaps. Newtons per coulomb. So this of course is to the right, just indicate that to the right. Is that right? To the left, sorry, that's to the left, it's in that direction, and then this is to the right. So obviously they are in different directions, so we can find the resultant electric field intensity. Let's call that E. The greater one is you can see from the figures that this is actually greater, so we'll have 7.347 exponent 6 minus this 1.35 exponent 8, and if you do the subtraction, you've got 1.2765. That's so 1.2765 times 10 to the negative positive 6 newtons per coulomb, and that's going to be to the right. So that's very important, because electric field intensity is a vector quantity. You've got to state the magnitude and the direction. So in this case, the right is the direction and the magnitude is this 1.2765 exponent 6 to the power 6 newtons per coulomb. Let's look at another problem. So we'll find the electric field intensity at this point B. Let's draw a force diagram. Assume there is a charge of +1 coulomb placed here. That's by definition what electric field intensity is, the force on a charge of 1 coulomb. So the electric field intensity due to A at this point is going to be in this direction to the right, since there is repulsion between positive and positive. So let's call that the electric field intensity due to the charge at A. Then the electric field intensity due to the charge at C, as you can see, this is positive, negative, so it's going to be attraction. So the electric field intensity due to the charge at C will also be in that direction. So the resultant will probably be in that direction because all the vectors are pointing to that direction. So let's go ahead and calculate the electric field intensity due to the charge at A. The charge is 5 microcoulombs, okay, 9 exponent, 9 times 5 times 10 to the negative 6, that's, to convert it to coulombs, the distance between A and B is 10 centimeters, so that's 0.1 meters squared. Okay, if you plug those into the calculator, you have 4.5 exponent 6 newtons per coulomb. Let's find the electric field intensity due to the charge at C. Oops, this has got to be C. The electric field intensity due to the charge at C. 9 times 10 to the power 9. 3 times 10 to the power negative 6. The distance between B and C is 5 centimeters. That's 0.05 squared. If you plug this into the calculator, you have 10.8 times 10 to the 6th power newtons per coulomb. So our resultant electric field intensity, or our total electric field intensity, or our resultant, let's call that E. It's actually going to be EA sorry about that, plus EC, because they're all in the same direction. So we'll have 4.5 exponent 6, then 10.8 exponent 6. Okay, if you do that, you'll have about 15.3 exponent 6 newtons per coulomb. So that's our resultant electric field intensity. Okay, I forgot to do this often. So this is to the right. Also, this is to the right. So all the forces are pointing to the right. So our final answer also is 15.3 times 10 to the 6th power. This is to the right. By convention, all forces to the right are positive, forces to the left are negative. Okay, let's have another problem. This time around we have a two-dimensional problem. We have forces in some kind, charges placed in some kind of triangular configuration. We want to find the electric field intensity at point C. So here we go. Assuming there is a charge of +1 coulomb here, let's see the forces acting at this charge. If that's our point C, the electric field intensity due to A, this is positive, so that's going to be repulsion. It's going to be in that direction. Okay, just to have this letter C, I'll bring it at another point. Okay, so there we go, the electric field intensity due to the charge at A. The electric field intensity due to the charge at B is going to be pointing in this direction towards B, because this is positive and negative. So that's going to be attraction. There we go. Let me introduce the y-axis and the x-axis just to help us in resolving the forces easier. So if I have this line here and then another line here, it's important to find these angles because we'll use them while resolving the forces. So this is an equilateral triangle. You can see this side is equal to this, is equal to this. So all the angles in an equilateral triangle are going to be 60. We don't need to do a lot of calculation there. The interior angle sum has to be 180, so each one of those angles has to be 60, 60, 60. That's from the properties of an equilateral triangle. So there we go, we have 60 degrees here, also 60 degrees there. So this is the electric field intensity due to the charge at B. Okay, so this is going to be helpful for us to find the resultant electric field intensity, because we will easily get the components of EA and EB in the vertical and horizontal directions. So let's find the electric field intensity. The electric field intensity due to the charge at A, that's going to be 9 times 10 to the power 9. That's the constant K. Then the charge is 5 microcoulombs, so 5 times 10 to the negative 6. The distance between A and C is 20 centimeters. This is an equilateral triangle, so that's 0.2 meters squared. If you put these values into the calculator, you get about 1.125 times 10 to the 6th power newtons per coulomb. Let's do that also for the electric field intensity due to the charge at B. 9 exponent 9 times the charge is -3. Okay, I don't need to indicate the negative. After all, we'll take care of the directions using this force diagram. So there we go, -6 divided by the distance between B and C is 20 centimeters. That's 0.2 meters. So if you put these values into the calculator, you have 6.75 times 10 to the 5th power newtons per coulomb. So there we go, we have these two forces. We can now find the resultant force. Let's begin with the forces in the horizontal direction. So the forces in the horizontal direction, I love to call this the x-axis. So the summation of forces or the electric field intensity in the x-axis. So let's see. The the component of EA in the x-axis is going to be, of course, EA is this 1 point, okay, let's just do it this way. We have EA cos of 60 degrees plus also EB is in the positive direction, since this is the positive x-axis, negative, positive, negative. We know that from the Cartesian plane. So plus EB times cos of 60 degrees, this angle here. So that's the resultant force in the x-axis. If we put in the values, EA is 1.125 exponent 6, then cos 60 plus EB is 6.75 exponent 5 cos 60. If you do the math here, put these values into the calculator, you get 9 times 10 to the power 5 newtons per coulomb. That's the resultant force in the horizontal. Let's find the resultant force in the vertical, in the y-axis. So I'll call that the summation of forces, or the summation of the electric field intensity in the y-axis. Okay, from this diagram, that's going to be EA, okay, EA sine 60, because that's in the positive direction, the component of EA in the positive direction, but EB is in the negative direction, so I just have to subtract that, minus EB sine 60. So put in the value of EA here, that's 1.125 exponent 6 sine 60 minus EB is 6.75 exponent 5 sine 60. Okay, just to have more space here. If we go ahead and do this, you have, if you do this on the calculator, you have about 9.81 exponent 5, okay, times 10 to the power 5 newtons per coulomb. So there we have the forces in the horizontal direction and the forces in the vertical direction. Let's do the final resolution here to find what the total force is. So the resultant force in the x-axis, is a positive force, so it points in this direction. That's 9 times 10 to the power 5 newtons per coulomb, and the resultant force in the vertical direction also is positive. So there we go, 9.81 exponent 5 newtons per coulomb. So our resultant electric field intensity, if I call that E, is going to be, by Pythagoras theorem, the square root, just have more space here, that's better, the square root of, okay, begin with the vertical, 9.81 exponent 5 squared, what's that going to be, plus 9 exponent 5 also squared. So the resultant electric field intensity here is going to be, oops, guess I made a mistake here in the values. Okay, so just a moment, let's correct that. This value is going to be different. Okay, there we go. The resultant force in the vertical direction is actually, if you do that on the calculator, it's about 3.8971 exponent 5, okay, exponent 5, 3.897 exponent 5. There we go, 3.897 exponent 5. Okay, that's better. So the resultant here is approximately 9.81 exponent negative 5. There we go, newtons per coulomb. Also, since this is a vector quantity, we've got to find the direction at which this force is acting. So to find the direction, you just have to find this angle alpha. Let's go ahead and do that. So also looking at that triangle, you can see that alpha is actually going to be tan arc tan of the vertical component, 3.897 exponent 5 divided by 9 exponent 5. Okay, so if you do this, have about 23.4 degrees. So our answer is that the electric field intensity, so I'll call that the E field intensity, is going to be the force, the electric field intensity, 9.81 exponent, this is not negative 5, okay, sorry about that, exponent 5 at an angle of 23.4 degrees to the horizontal. Okay, so let's recap for this problem. It's quite a long one because it's in 2 dimensions. So the most important part is to extract the force diagram, a correct force diagram from the configuration of charges. After finding these forces, resolve to find the total force in the x direction, the horizontal direction, and the total force in the vertical direction. Then we draw a separate diagram for only those 2 forces. That helps us to find the total or the resultant electric field intensity. So using Pythagoras theorem, also using simple rules of trigonometry, basic trigonometry, you can find the direction of that force, and there we go. Okay, let's have another example. Okay, this example, we have the same thing. We have A, B, C. So let's indicate the charges here. The charge at A is actually 0.1 microcoulomb. The charge at B is 0.05 microcoulomb. So we want to find the electric field intensity at C. Okay, this is a 2-dimensional problem, so let's draw also a force diagram here. For simplicity, I always put a +1 coulomb charge here. So between 0.1 and 1, all these are positive charges, so the direction is going to be the direction. Let me call this the electric field intensity due to the charge at A, it's in that direction. Then the electric field intensity due to the charge at B, this is positive, this is also positive, so it's in that direction. There we go. The electric field intensity due to the charge at B. So let's go ahead and include our y-axis and x-axis just to make it easier for us to resolve the forces. Also, let's find these angles. They will be helpful. So if I draw this this line here, that means we have 4 centimeters here. So these are 5 centimeters, 5 centimeters. I can find what this angle here is. Let's go ahead and do that. So let's call this angle theta. That angle theta is the same angle here and is the same angle here. So let's calculate what that angle theta is. Theta from this diagram is going to be from cos arc of 4/5. Okay, cos arc of 4/5 which is what's that, 36.9 degrees. Okay, 36.9 degrees. So we have 36.9 degrees here, 36.9 degrees here. That's going to be very helpful. Okay, let's calculate the electric field intensity due to A. That's going to be the electric field intensity due to the charge at A, 9 exponent 9. The charge is 0.1 times 10 to the negative 6th. The distance between A and the point C is 5 centimeters. So that's 0.05 meters squared. If you plug those values into the calculator, okay, you can go ahead and do that. So we have about 3.6 times 10 to the 5th power newtons per coulomb. The electric field intensity due to the charge at B is 9 exponent 9 times the charge 0.05 exponent negative 6 divided by the distance, which is also 5, 0.05 squared. That's about 1.8 times 10 to the power 5 newtons per coulomb. So let's use these two values to find the resultant electric field intensity. So let's find the electric field intensity in the horizontal direction, in the x-axis. The summation of electric field intensity in the x-axis will be EA cos 36.9, because that's in the positive x direction, minus EB cos 36.9. Okay, that's degrees. Anyway, so go ahead and put in the value of EA here, the value of EB there. Let's see what we have. EA is 3.6 times 10 to the 5th power minus EB is 1.8 times 10 to the 5th power cos 36.9. That's about 1.45 newtons per coulomb. Let's also find the resultant electric field intensity in the vertical direction. That's going to be EA, let's begin with that, EA sine 36.9 plus, because all of them are pointing, all the components are pointing in the positive y direction, so that's plus EB sine 36.9 degrees. So let's substitute the values. So let's substitute the values. We have EA, that's 3.6 exponent 5 sine 36.9 plus 1.8 exponent 5 sine 36.9. So if you put these values into the calculator, let's see what we have. That's about 3.24 exponent 5 newtons per coulomb. So let's use these two, okay, these two results, this and this, to draw a force diagram, a final force diagram representing the vertical and horizontal component. So our vertical component is positive, there we go, 3.24 exponent 5. Our horizontal component is also positive, 1.45 exponent 5 newtons per coulomb. So our resultant electric field intensity will be in that direction. and it's equivalent to the square root of 3.24 exponent 5 squared plus 1.45 exponent 5, oops, okay, that's squared 2, that's about, let's see what we have, 3.55 exponent 5, that's newtons per coulomb. Okay, that's the electric field intensity due to the two charges. Let's find the direction, call that direction beta perhaps. So beta is going to be tan arc of the vertical component, 3.24 exponent 5 divided by 1.45 exponent 5, and that's going to be about 65.9 degrees. So the resultant electric field intensity, in this case, the electric field intensity is going to be this 3.55 exponent 5 newtons per coulomb at an angle of 65.9 degrees to the horizontal. Okay, there we go. Let's have a final problem on electric field intensity. So here we're having a rectangular configuration. Okay, still a two-dimensional problem. We want to find the resultant electric field intensity at this point S. Okay, let's draw the forces at point S. Of course, we assume there is a charge of +1 coulomb here. So let's begin with R. This is a positive charge, and this is a positive charge. So at R, there's going to be a repulsion electric field intensity in that direction. So that's the electric field intensity due to R. Okay, let's look at in this direction. This is negative, this is positive. Yeah, so there's going to be attraction. Is that so? Yes. Okay, yeah, that's it. So the electric field is going to be in that direction. Let's see due to the so this is the electric field intensity due to P. Let's see the electric field intensity due to Q. As you notice here, so this is a positive charge, this is positive, there's going to be repulsion. So the electric field intensity due to Q is in that direction. This distance, okay, let's check the question. This distance is 3 centimeters. This distance here is 5 centimeters. 4 centimeters, sorry. So by Pythagoras theorem, you can calculate this distance. If you have 3 here, oops, just make this better. If you have 3 and 4, then this is 3 squared plus 4 squared under a square root. So that's going to be 5 centimeters. Okay, so let's have that 5 centimeters. Also, we could find this angle here. Let's call that angle alpha, because that's going to be very useful in resolving. We've got to find what this angle is. Just prolong this a little with this angle here. So let's call that alpha. Let's see how to find alpha. We have every alternative we could ever want. So let's just say alpha equals arctan of 3/4, and that's going to be, okay, that's 36.9 degrees. Okay, let's go ahead and find the electric field intensities now. So that's 36.9 degrees. Let's begin with the electric field intensity due to P. The electric field intensity due to the charge at P, the negative 3 microcoulomb charge. So that's 9 exponent 9 times 3 exponent negative 6, because that's, these charges are in coulombs, very important here. So no need to convert. That's 3 exponent negative 9 here, as it is given here. This is already in coulombs. The distance between P and S is 4 centimeters. This is a rectangle, so this is the same as this. This is equal to this. So that's 4 centimeters, 0.04 meters squared. In this case, the resultant, the electric field intensity due to P is 1.687 exponent 4 newtons per coulomb. Let's do that for the electric field intensity due to Q. That's 9 exponent 9 times the charge at Q is 4 exponent negative 9. That's actually 4 nanocoulombs. The distance is 5 centimeters, so 0.05 squared. Okay, let's see, what do we get there? Put this in the calculator. It's 1.44 exponent 4 newtons per coulomb. Then the electric field intensity due to R, that's 9 exponent 9 times the charge at R is 3 times 10 to the negative 9 divided by the distance. The distance is actually 3 centimeters, 0.03 squared. If you do this, you have 3 exponent 4 newtons per coulomb. So let's find the resultant force in the x-axis, the resultant electric field intensity. Okay, that's going to be negative EP, because that's in the negative direction. ER has no horizontal component, so we don't have any component in the horizontal, plus we have EQ cos 36.9. so EQ has vertical and horizontal components. The horizontal component is that. So if you put in these values, so I'm not going to do that for this, but if you put in these values, actually have negative negative 5.355 times 10 to the positive 3 newtons per coulomb. The negative here shows you that the resultant is actually pointing in the negative direction. If you do that for the resultant force in the horizon, the resultant electric field in the in the vertical direction, so the summation of forces in the y direction, you have the resultant, the electric field intensity due to R plus the electric field intensity due to Q sine 36.9. So as you see, the electric field intensity due to Q has a vertical component in the positive direction. If you put in the values here, you'll have about 3.865 exponent 4. Okay, there we go, newtons per coulomb. So let's draw a final force diagram to find the resultant electric field intensity. Notice that this is in the negative direction, so our force diagram looks like this. We have 5.355 times 10 to the third power, so that's in the negative direction. I don't need to put the negative here again. This is positive 3.865 times 10 to the fourth power. There we go. Our resultant electric field intensity is here, and that's going to be the square root of 5.355 exponent 3 squared plus 3.865 exponent 4 squared. If you put this into the calculator, I'll have about 3.9 times 10 to the 4th power newtons per coulomb. Okay, there we go. Let's go ahead and find the direction of this force with respect to the horizontal. Let's introduce an angle, maybe theta. So theta is going to be arctan of the vertical, 3.865 exponent 4 divided by 5.355 exponent 3. That's about 82.11 degrees. Okay, so our final answer here is that the electric field intensity is 3.9 times 10 to the 4th power at an angle of 82.11 degrees to the horizontal. Okay, that's perfect.